I mentioned a few minutes ago, if this looks like this is really redundant, that's great. Let's think about the sorts of groups that we can now react to Grignard reagent with. And let's keep score up here in the upper left. So we're going to think about aldehydes, ketones. How about something different? How about carbon dioxide? Epoxides. And let's put it over here, 5. Later, esters. Finally, 6, how about an acyl chloride or acid chloride? RIDE, chloride. So just to help organize things. So how about first, let's think about within an aldehyde. And let's use the simplest aldehyde as our example. So spell it right, formaldehyde. We'll use some Grignard reagent. Let's just have maybe 3 carbons, make it a little bit shorter to squeeze it in there. And let's react this with, try that again, formaldehyde. And we'll do this in the presence of ether as our solvent. I'll just write ether now. Well, when we think about the mechanism of this, as we've seen now, this carbon has this is kind of small. I'll make the next one bigger. A dipole, so this carbon is our electrophile of the aldehyde. Formaldehyde, it has 2 hydrogens here. This is our aldehyde. It's a special case where both sides have a hydrogen, but the reactivity is going to be the same. And we're thinking about this, sorry, back to the back here, as carbon negatively charged, magnesium bromide positively charged. And what I didn't mention before is our whole positively charged species is the magnesium bromide. You could balance out that, or you can calculate the formal charge. You'll see it's a positive one. So our species now is actually going to attack here, and I'll use the bottom one here. Move the electrons up onto this oxygen, forming our tetrahedral intermediate. O minus, hydrogen, and we've added carbons. And we want to keep track of the number of carbons. Notice here on the bottom, I'm counting it. We've added 1, 2, 3 carbons, or the same thing here. This is carbon 1, 2, 3. That's the carbon that's connected to the magnesium. So we don't want to add or subtract carbons. 2, 3 carbons that we've added. And to balance this now, the magnesium bromide is going to be coordinated to the oxygen. And now we do not have a good leaving group because we have 2 hydrogens here in this alkyl chain. So now what we're going to do is let that reaction happen, wait around for a while, and then later on, just carefully add in a small amount of dilute acid. So it could be water with just a touch of sulfuric or hydrochloric acid, which is then going to be used to protonate this. And I was wondering if I left enough space, so I'm going to go down just a little bit. Form our alcohol. Added our carbons. And then we're going to end up with magnesium bromide here. And then let's just put a chloride there. So let's say we use just a little bit of HCl or even ammonium chloride. This is a detail here, not the main part of the reaction, but just something to add in here. Okay, so then the key thing here is to note that we went from formaldehyde here on the left to, on the right, an alcohol, and it's a primary alcohol. 1, 2, 3, 4, it's actually butanol. It's 1 butanol that we went to. Primary alcohol. We don't have to worry about stereochemistry because that carbon that now was once part of the carbonyl group is not chiral. That was exciting. Let's do one more with formaldehyde. We'll stick with the bromine. So let's take this species here. Now we have, rather than an alkyl Grignard reagent, let's use an aryl, A-R-Y-L. And let's react this again with formaldehyde in the presence of ether. I notice this is not supposed to be some fancy BR, it's just they couldn't draw it. Let's try it again. Slowly. BR, okay? Now, in this particular case, our imaginary Grignard reagent is we're thinking about as really carbon with a negative charge here. That seems unusual. MgBr plus. But that's going to act as our nucleophile. These are the top one here now. So this is going to attack here our electrophilic carbon, move these electrons up onto this oxygen to form our tetrahedral intermediate. And now we're going to end up with a species. Let's draw the ring first. So now we've added to this carbon, the hydrogen, and the hydrogen. You could draw the benzene ring dangling down below. That's fine too. I'm just trying to show it in the different ways that we might see. Let's stay with that. And now the last step, let's protonate. Here's our generic acid. So a pretty poorly drawn ring. Not sure why they have those little flourishes on it. Let's try that. It's close enough. Primary alcohol again. Or you'll see MgBrOH. We'll be ignoring that probably from here on out. Now, one or two other things with this reaction here is if you look in the textbook, or if you already have, or when you do, you'll notice that this mechanism, let's use the bottom one, is shown a little bit more complicated in the book, where they have this magnesium coordinating to the oxygen at the same time as that this carbon is attacking. That's probably correct as well. I simplified it a bit. I think this is sufficient, and it focuses on the main bond that's being formed. And so this is okay when drawing the mechanism, if one is asked to draw the mechanism. This is the more common way of showing it. It actually probably leaves out a little bit of detail, but I think it's okay, and it gets the main point across. And so if you see it in the book and it looks a little bit more complicated, if you want to draw it like that, by all means, that's fine, but it's not necessary. Okay, so then as we're going through this, with that, this is also a primary alcohol. Not to belabor the point too much, let's consider, how about an aldehyde or a ketone? Let's scroll this up further. Let's use the same benzene, just Grignard reagent that we had made. Let's react this now with about this aldehyde in the presence of ether. So I'll put the plus there. Aldehyde, ketone, let's use the same one. By one, I mean the Grignard reagent. How about just acetone? Ether. So I'll pause for a second, and I'll just ask you to please just draw the products of those reactions, and as well as the mechanism, if you would please. And there's nothing meant to be tricky. If it looks just like the ones above, it is. So I'll be quiet for just a minute as we do this. hopefully everyone had time to come up with something. So hopefully we'll see that it's the common mechanism. So we have our electrophilic carbon on that aldehyde. It's going to attack as a nucleophile. Move these electrons up onto the oxygen, forming our tetrahedral intermediate. Let's keep this all the same. O minus. We have a hydrogen and a methyl group. We do not have a good leaving group. So we'll wait until we add a splash of our acid. And we're going to protonate this. Now for this one, notice when we protonate it, we're going to end up with a secondary alcohol. But we're going to have on our alcohol the OH group, a methyl group, a hydrogen, and then the benzene ring. So we actually have 4 different species. So we could have something where we could put it like this. Plus, let's just keep the benzene in the same spot. See if we can squeeze it in. It's close. Hopefully it fits. And the hydrogen there. So we'll have our racemic mixture. All right, so then notice now that is a secondary alcohol. And then this is the same thing with the ketone. It's going to attack. I'm just going to form our tetrahedral intermediate. This time now has 2 methyl groups, which are both the same. Go ahead and protonate. Form the species. And I should actually put in the magnesium bromide up here on these. I think I left that off here. Okay, so I'm filling that in, putting in that magnesium bromide. So those are all examples with the alkyl group. How about, an aryl group. How about with an alkyl? Grignard reagent, same idea. So let's use something a little more complicated. Let's have this species here. And let's react this with this acetone in the presence of ether. But mechanistically, if we wanted to predict the product, same idea. This is going to nucleophilically attack the carbonyl group, form a tetrahedral intermediate. And let's just have, so 1, 2, 3 carbons, 1, 2, 3 carbons, O minus here. And then we'll simply protonate. OH, and those 2 methyl groups. This one happens to not be chiral. But if we add a chiral center, we'd end up forming our 2 different species. So while the reaction products are becoming more complicated in terms of the structure, the idea is that it's just essentially the same mechanism over and over. Scroll back up for a minute. And we can see, so we've covered our aldehydes up in the upper right corner. We've got aldehydes and ketones. And we'll see that for these other functional groups, the reactions essentially, it's the same idea. So let's take our last few minutes here. Let's look at the carboxylic acid and maybe the epoxide as well.